So, on this section of the video, we are going to be talking about the HL kinetics. And so this is HL. And so this is topic 16 for those of you keeping track in your textbook or in your syllabus. And what this focuses on is really three main ideas. One, mechanisms, talking about elementary steps in a reaction, which then leads us to rate law expression and rate order. And then, last but not least, we will talk about the Arrhenius equation. Okay. Now, it seems like only 3 bullet points that it wouldn't take a long time, but the rate law expression one takes quite a bit of time to explain because you got to talk about the graphs, you got to talk about every individual order, and then how you would actually calculate the order of the each reactant in the rate law expression itself. So, while these bullet points don't seem that intimidating, there's a lot of stuff that we need to talk about with them. Okay, and so the first thing we'll talk about is mechanisms. Okay. So if you remember in SL, we talked about collision theory said only 2 particles can collide with each other to initiate a reaction. And so if you have something like this, because there's 3 particles that are reactants, according to our collision theory, there's no way this happens in one step. There's no way that all 3 particles collide together and form one particle. And so what this is essentially a reaction like this must occur in multiple simpler steps, okay? And those are called elementary steps. And the sum of the elementary steps overall to get the overall reaction is known as a mechanism, okay? So the mechanism is the explanation of all the elementary steps to accomplish the overall reaction. Okay. And as we talk about this more and more, mechanisms are all experimentally determined, and there is possibly more than one correct answer to explain how a reaction occurs, even based on the data that you get. So while there are right and wrong answers for how it reacts, there could be more than one right answer. That still completes our concept here. Okay? So let's say that a reaction here, 2A plus B yields C, could be broken down into a multitude of different steps here. Maybe your 2A particles collide together to form D, and then D collides with B to form C. Yes, Pancho?
Is this where we did the whole rate determining step thing?
A little bit, yes. When we get into rate law expression, we'll connect it, we'll tie it to this, yes. So this does have to do with rate determining step, okay? But I won't go back to that until after we've done rate order and things like that, because then it'll make more sense, okay? Now, this suggested mechanism makes sense in the sense that when you add these 2 reactions together, you end up getting 2A plus B yields C, okay? And in this scenario, D is known as an intermediate, okay? An intermediate is any substance that is produced and then used up, so therefore it has no net impact on the reaction. So an intermediate is produced then used. So it won't appear in the overall reaction. Yes, Tyler?
Is there any way to intervene after that first step so that you can have an intermediate? Like stop the reaction?
No. So that's a good question. In these types of mechanisms, things like that, there is generally not a way to stop or halt the reaction in that middle step. No.
So is that middle step basically instantaneous then?
Yes.
Okay.
So with these intermediates, usually the intermediate production is extremely quick. And so sometimes scientists can't even decide on what the intermediate molecule is. It's just they just know there is an intermediate. Okay? Now, an alternative for this reaction very well could be something like this. A plus B yields, I guess, D as well, and then D plus A yields C. This mechanism still would technically work along the lines of that it adds up to 2A plus B yields C. So both of these are possible mechanisms. Now, once we experimentally collect data, we will be able to eliminate one of these choices, and we'll kind of talk about that a little bit later. Now, one other thing in mechanisms that may show up, okay? And this is we'll kind of draw a line here, so this is kind of an aside to mechanisms. But so, let's say we have a reaction like this, okay? Now, the overall reaction here would be A plus D yields C plus E. So, C, we've already established, is an intermediate. B, on the other hand, is not an intermediate. It is being used up and then being produced here. Okay? So it is the opposite of an intermediate, and the name is not really opposite. B is actually what's known as a catalyst, because B is providing an alternate pathway by reacting first and then being produced, so that there's no net change in the amount of it. So B is a catalyst. So if you are using it and then producing it, that's a catalyst. If you're producing it then using it, that's an intermediate. So make sure you differentiate between that. Yes, Mohammed.
Why do you write C in the overall equation?
Oh, sorry. You're right. That's a typo. I just saw the C. Yes, there's no C. Thank you. Because the C's cancel out. So it's A plus D equals C. This is where if I was really trying to edit this, I would edit that part out so I didn't look so dumb. Okay, but I don't really care. See ya, Mohammed. On that note. I feel like he's been sitting there for an hour and a half saying, let me find when he makes a mistake so I can walk out with my crap. Like, I think that's what he's been doing this whole time. Okay, so there should be no C. Okay, so A plus D yields E is the overall reaction. So a catalyst and an intermediate and how they behave in this scenario. Mm-hmm.
Can you say the difference between
Sure. An intermediate is something that's produced and then used up later on, so that you don't notice the its existence in the reaction. A catalyst is used up and then produced again, so you started with some catalyst and you end up with the same amount of catalyst. But in intermediate, you started with no intermediate, you made it and then used it up, so you ended up with no intermediate as well. Does that make sense, Melissa? Okay, you're welcome. Now, these individual steps here have what is called molecularity, okay? And so when you have a step that's, let's say, A yields B plus C. When you have one reactant molecule, this is called a unimolecular reaction. Okay? Whereas if you have two particles, that is called a bimolecular reaction. That's the molecularity of a reaction. So if they ask you what is the molecularity of the elementary step, you would say unimolecular or bimolecular. Again, you can't have a trimolecular, because the collision theory states that that you can only have two particles colliding together. So either unimolecular or bimolecular elementary steps. questions about that. Okay, we will go back to this after we do rate laws and see how our mechanisms have to match our rate law experimentally. So once we explain that, you'll kind of see what that is. Okay, so that's bullet point 1 for now. Bullet point number 2 is rate order / rate law expressions. Okay, so if you remember, okay, so rate order is essentially the impact of a change in concentration on the rate. And it's a mathematical impact, okay? And so you can have 3 scenarios with how the change in concentration of a change in concentration affects the rate, okay? There is what's called a 0 order, where if I graph the concentration of that substance versus time, the change will be consistent. Meaning that no matter what the concentration of A is, the rate of reaction will be the same, because the rate of reaction here is the slope. Okay? So in a 0 order, that means 0 means that's the exponent, and that means that no matter what the concentration is, it will not change the rate of reaction. A first order reaction means that whenever I change the concentration, I change the rate by the same amount. Okay? And so here I have it like this, where I start with a large amount of reactant, and as I go down, the slope changes with time. Okay? But there is a relationship between that. Yes, Amir?
So, Mr. John, to calculate the initial rate of reaction, where do you take it from?
You take it from, usually time is 0.
Okay.
So you draw a tangent to time equals 0. Okay. So in this scenario, whatever factor I change A by, that changes the factor of the rate. And we'll kind of see that in a graph in a second. A second order reaction means that if I change the concentration, I actually change the rate of reaction by an exponent of 2. So therefore, the curve will look much steeper than the first order. So the rate at which the rate of reaction changes happens much, much more quickly. And I'll tell you a trick to differentiate between those two in a little bit. Okay. Now, you not only have to know the graph of concentration versus time, but you also have to interpret that into the graph of rate versus concentration, because that's what you actually care about. You actually care about how does my rate change with concentration.
Mr. Trump?
Yes?
On the first order and second order, do they touch the axes?
I guess you're approaching 0, essentially.
No, and the concentration. They do touch the y-axis, they don't touch the x.
Yes.
Okay.
Yes, sorry. So let me ask you this. On 0 order, does my slope change anywhere on my concentration versus time? No. So my rate should look like what? Straight line across, horizontal line. So here, it is a horizontal line here. Okay. In a first order, mathematically it turns out that when I double my concentration, my rate also doubles. So what does my graph look like now? Like, how do you show a direct relationship between two species? Yes, Ginevra?
Is it like a diagonal?
Yeah, diagonal line, right. And so I like the arm motion. I wish the video captured that. Okay, it's just kind of like that. Okay, so the rate here looks like this, where if I double, if I double the concentration, then I will double my rate as well. Okay. In a second order, it turns out that, when I double the rate, I double the concentration, the rate quadruples. Okay? So therefore, anytime I do something to concentration, the impact on the rate is actually the square of that change. So if I double concentration, I will quadruple the rate of reaction. Or if I triple the concentration change, I will 9 times the rate of reaction. Yes, Pancho?
No.
Okay. So how do I graph a relationship between something and then the square of something else? It's a parabola. Okay? So it's an exponent, right? So it'll look like this. Because as I increase my A, the rate will actually exponentially increase. Giselle? Oh, I thought I saw your hand up. Okay.
Can you go over again why it's the rate and the concentration? I thought it was rate over time.
No. So these are two different graphs here that we have to kind of translate. And so the first graph up there shows change in concentration versus time. Okay? And to figure out the rate based on that graph, you have to take the slope of that graph. The second graph is, I want you to take the slope of that graph at every concentration and then plot those points on a graph. So I've changed the axes there. And there is a differentiation between these, and you have to know all 6 of these graphs. Okay? What I like to think about is that these graphs are probably the ones that you really want to focus on, because these graphs actually are based on the equations that you need to know. Because we have expressions for each of these equations. Okay? And so this graph right here is represented by the equation rate is equal to k times a to the 0 power. Okay? And this is called a rate law expression. Okay? Where k, lowercase k, is the rate law constant, which we'll talk about calculating a little bit later. Okay? In a first order, rate is equal to k times a to the first. And in second order, rate is equal to k times a to the second. Okay? That's why the graphs make sense the way they do, because in this equation right here, if you double a and you plug in 2a here, you have to square it to get the rate. So then it becomes 4a squared here, and then that ends up being your rate. So your rate has increased by 4 times. Yes, Chloe?
Could you give like an example for the 0 order?
Oh, like a real life example?
Yeah.
Most reactions end up following the first order reaction. They won't ever ask you for an example of that. I can't think of one right off the top of my head about a 0 order reaction, because it had to be something that no matter what would just, I can't even off the top of my head think of an example of one that's a 0 order reaction, where the rate wouldn't depend on the amount. Okay. So, wait, what?
I asked them why did
Oh, okay, sorry. So the reason, that's a good question, Muffet. The reason why it exists is because when you have multiple reactants, some reactants don't have an effect on the reaction. So in the problems that we're going to do, we're not just going to do one rate order. We're going to do an expression with 2 or 3 reactants. And it is completely possible that one of the reactants has no effect on the rate, but the other ones do. So, like, I can't think of a reaction that only has one reaction that says, okay, this is 0 order. But I know reactions where there's 3 reactants and one is 0 order, one is first order, and one is second order. So that's the reason why you show up with these. Okay? And so if you understand what 0 order, first order, second order mean, then you don't have to memorize these 3 graphs, because these 3 graphs are just these equations. Rate equals k. So guess what? The slope of this is k. Rate equals k times a. That's y equals x. Y equals x. This is y equals x squared. What does y equal x squared look like? This. So you don't have to memorize these graphs. I would know these top graphs here because you do need to kind of represent them. Now, I said earlier that you would be able to figure out the difference between a first order and a second order. The reason why you can is this. I'm going to put a picture up here that's easier to kind of interpret because I think it's easier to kind of determine this off of that. But so, let's see. A first order graph looks, where is it? Wait. Oh, maybe I have it in graphs. Hold on. Wait, where is it? Oh, here it is. Okay. Let's see. First order graph versus second order graph. Okay. Now, this is first order on the left and second order on the right. Okay? The thing with first order is there's a concept that we talk about with reactions known as half-life. Okay, you might have talked about it in physics. You may have heard it even in biology when you're talking about kind of carbon dating and stuff like that. But so half-life is the time it takes for the concentration to be halved. Okay? Most radioactive isotopes have a half-life. It has a certain amount of time it takes before the isotope becomes half the mass that it was before. Reactions have that same thing with concentration. It turns out that if you do a half-life for a first order reaction, let's say you do 0.16 to 0.678, 0.08, this time at 0.08 to 0.04, those times are approximately 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. They're the same. So if you find the half-life of 2 different sets of points, the half-life in a first order is constant. Because every time you halve the concentration, the rate also halves. So it takes the same amount of time. It's like saying, how long would it take you to drive 60 miles at 60 miles an hour versus how long would it take you to drive 30 miles at 30 miles an hour, right? Because you're halving the amount and you're halving the rate. So it takes the same amount of time. So your half-life is consistent in first order. The problem in second order is what you're saying is, I'm going 60 miles at 60 miles per hour, and then I'm going 30 miles at 15 miles per hour. Because my rate changes more quickly than my concentration does. And so with this in a second order, the half-life will actually increase as you get smaller and smaller. So like if I pick, let's say, 0.14 to 0.07 versus, I don't know, 0.678, 0.9 to 0.45, notice my time has gotten longer. And so they don't have to be half of each other. You can just show by any two halves. So pick any 2 points that are half of each other and see how long it takes. And so for second order here, going from 0.14 to 0.07 takes you, let's see, 20, 40, 60, about 90 seconds. But going from 0.09 to 0.045 takes you 20, 40, 60, 80, 100, 110 seconds. Okay. Also, really pay attention to those units down at the bottom of your axes, because the IB will try to catch you not paying attention to that stuff. So pay attention to units. So here, half-life increases as concentration decreases.
So in these terms, half-life is just referring to having the concentration that you're at, not
Correct.
the total.
Correct. Just any point to any point, that's half of it. Okay. So all radioactive reactions follow a first order reaction. I mean, that's why we can do carbon dating, because carbon-14 follows a method where every 5,900 years, half of the carbon-14 will be disappeared. So scientists, essentially what they do is, we know how much carbon-14 is associated with carbon-12 in all life forms. Like, we know the percentage. So the carbon-12 doesn't go away though. So if we take a sample of a substance and we measure how much carbon-12 there is, we know how much carbon-14 there should be. And if we know how much there should be and we measure how much there actually is, we can figure out how many half-lives it's gone through, so we can figure out the age of something.
When you say should be, the amount of carbon-14 it had when it was alive.
Yeah, because we know the ratio it should be.
Yeah.
So let's say, for example, I have 99 grams of carbon-12 in my sample, and I know brand new I should have had 1 gram of carbon-14. But now my sample has 0.25 grams of carbon-14. That means it's gone through 2 half-lives, from 1 to 0.5, and then 0.5 to 0.25. So therefore, it's approximately 13,000 years old, or 12,000 years old, sorry.
There you go.
So know these graphs. It's a very common multiple choice question. Sometimes I'll have you sketch them on short answer as well. Okay. What we haven't done yet is, how do we calculate those exponents? How do we know based on data what those exponents are? And that's what we're going to talk about now. Okay. And the key thing here is you want to emphasize is that exponents can only be determined experimentally. You cannot look at a reaction and say this is first order or second order. There's no, when you have more than 2 particles in the reactants, there's no way you can do that. Okay. And so what we're talking about here is the idea of a rate law expression. Okay? A rate law expression essentially relates your rate to your rate order and rate law constant. And remember, expression, not equation. Okay, so expression doesn't have any numbers in it. It's just mostly variables. Okay, so rate law expression looks something like this. Rate equals lowercase k, a to the m, b to the n, c to the p. Okay, where lowercase k is the rate law constant. That's the fixed constant for the reaction, and that changes based on reaction. Units vary depending on the orders. Okay? M, N, and P are the order of reaction with respect to A, B, and C. So M, whatever exponent that is, you would say that's the order of reaction with respect to A. So if M is 1, you would say A is first order. If N is 2, then B is second order. If P is 0, then C is 0 order. If you add them up, M plus N plus P, That's your overall rate order. So adding all the exponents together gets you your overall rate order. And then just A, B, and C are your concentrations of those substances in your reaction. So figuring out these exponents is essentially a system of equations. You're given data, and by using your data, you can figure out what those exponents are. Okay? And so, for example, let's say I have a reaction of A and B and the rate of each of those experiments. And I say A is 2 molar, and then it's 2 molar, and then 4 molar. And B is 1 molar, 2 molar, and then 2 molar. And I say the rate is 4 molarity per second, 16 molarity per second, and then 8 molarity per second. Let's pretend that's a set of data that I have. So I did all these experiments and varied these things and measured the rate. Okay. I'm going to do it the long way first, essentially, I guess I would say the foolproof way, and then I'll show you kind of a shortcut after that. But I want you to see the foolproof way first, and then do it the other way second. Because I want to make sure that in case you kind of go blank, you can kind of always fall back on this. Okay. What you need to understand is that this is the same reaction. All 3 trials are the same reaction. So, therefore, the rate of, let's say trial 1 and its K value and its A value and B value is proportional to the rate of trial 2 and its K value and its A value and B value as well. Okay. Yes, Chloe?
Is this always the case, or is this just...
No, this is always the case. Sorry, this is always the case. So this is kind of the foolproof way. Now, mathematics tells you that the only way you're going to be able to solve something is if you only have how many variables? 1. So we've got some issues here. We've got a bunch of different things kind of floating around. Good news, we have the rates. Also good news, we have A's and B's. The K is the same, so that will do what? It'll cancel out. So K doesn't matter. Okay? So we're trying to solve for M and N here. Okay? What do you think needs to be true so that we can solve for M or N? It doesn't matter which one, but what needs to be true about the concentrations of one of them?
Has to be the same.
It has to be the same, no, right? Because if the concentrations of A are the same, then this cancels out, and you're left with B and just N as the exponent you're solving for. If the B's are the same, then those cancel out, and you have M that you're left to solve for. Okay, do y'all see where I'm doing that? So your goal is always to try to find 2 reactions where one of the variables is changing and all the other variables are the same, huh?
Because I never knew why we did that.
Yes. Okay, so I set this up so it works very easily. So I'm going to plug this in. So rate 1 is 4. Rate 2 is 16. A, in this case, is 2 to the M, and then 2 to the M. And then B is 1 to the N, and 2 to the N. So 2 to the M over 2 to the M cancels out. So I'm left with 1/4 is equal to 1/2 to the N power. Does everyone see how I got there?
Yeah.
I plugged in numbers, things that are the same cancel out. I should be left with one variable. At this point, it should be pretty straightforward because n must be what? 2. So b is second order with respect to, it's second order with respect to b. Okay. Now, which experiments could I now do to solve for a?
I mean, you could do 2 and 3.
You could do 2 and 3.
But does it matter now that you know n anyway?
Okay, that's a good point, Tyler. So the easiest one is 2 and 3 because that doesn't depend on n because b's are the same. But Tyler brings up a good point. Because we know the exponent for b, it doesn't matter which 2 we do as long as a changes.
Yeah.
Right? So we could do, since we know b, we could do 1 and 3.
But you can't do 1 and 2 because
You can't do 1 and 2 because a doesn't change. Exactly. So you could do 1 and 3 or 2 and 3 in this scenario because we know what b is. Now, is 1 and 3 a little more complicated because you have to remove b's impact on it? Yes. But you could still do it. Okay? And there may be a case where you might have to do that. And that's what Tyler brings up as a good point. Because the IB, if I'm the IB, I'm going to give you like 3 reactants. And I'm going to give you some times where B is the same and sometimes where A is the same. And you know what I'm going to do with C? I'm going to have it so there's no 2 experiments where A and B are both the same and C is the only one that changes. So that means you have to figure out A's exponent and B's exponent first and then apply those to solve for what C's exponent is. So that's how I make it more difficult. Okay? So here, I'm going to do the simple, actually, I'm going to do the hard way. I'm going to do 1 and 3 because that way you can kind of see what I'm talking about here. So 1's rate is 4, 3's rate is 8. A for 1 is 2 to the m, B is 4 to the m here. A, sorry. And then B is 1 to the squared, and then B here is 2 squared. Okay, so this is rate 1 and rate 3, if we're keeping track here. So now I simplify. 1/2 is equal to 1/2 to the m times 1/2 squared. Uh-oh. I think I've actually messed this up. Wait, did I actually mess this up? Oh, okay. So my numbers don't work, do they?
Yeah, I just did 2 and 3 and it gets
Concentration of A.
2.
Okay. So I just realized, okay, let's go back.
Is there like a negative order?
Let's change that to 32. Okay, that's my fault. Okay, let's change that to 32 and now it'll work. Because I was trying to make the numbers up on the fly and then I got ahead of myself. So let's redo this. So this is 32 and that's 1/8. This will work now. And this will work with 2 and 3 as well. I should have checked 2 and 3 before I made up those numbers, but lesson learned. So this is 1/8 is equal to 1/2 m times 1/4. So now we remove B's impact and we end up getting 1/2 times 1/2 to the m. So m is what? 1. So now we know both orders. So we could say the rate law expression is rate is equal to k times a to the first and b to the second. Questions on how I solve for all of that? Okay, any clarifications that y'all need?
What's K again?
K is the rate law constant. So that is unique to every reaction. And we will have to solve for that, which we will do next.
And that's Arrhenius.
I'm sorry?
Arrhenius, whatever.
No, that lowercase k is in the Arrhenius later on, yes.
That's not how you find those.
No, it's not how you find it. Okay. Now, if you want the shortcut method, it's really not it is a shortcut without having to write as much work, but it's still the same idea. But I'm only showing you this because 90% of the time it works, but then the issue is when it doesn't work, so you have to kind of be careful. But if I'm doing this kind of in my head, I just look and find the reactions where something's constant and see what's left. So like I look here and go 1 and 2, A is constant, B is doubled, and rate is quadrupled. So if B is doubled and rate is quadrupled, then the exponent must be 2, because 2 to the x must equal 4. Here, this is doubled, this is the same, and this is doubled, so they're directly related, so it must be first exponent. That's probably the way you learned it last year.
Yeah.
But you didn't understand why you were doing it, right? So that's why I showed you that way first.
Wait, can you say that again?
Sure. On the second part?
Yeah.
Yeah. So in reactions 2 and 3, this doubles,
Okay.
and this stays the same, and this doubles. So this doubling is due to A's doubling. So the exponent for A must be 1 because it does the same effect. It has the direct impact on that. But for B, it doubles and the rate quadruples. So that means that if you double the rate, double the concentration, then there must be an exponent of 2 so that it affects the rate correctly. Yes, Tyler?
And the only way it wouldn't work is when you don't have a constant for both.
Correct.
Or two
Then
constants for your
that's
A.
when you fall back to this. Now, technically, you could still do the shortcut way and divide the impact of the other ones, but I like this way. It minimizes mistakes.
And if it's 0 order, then from 2-1 you would just go to 4-1 and be 4. So like nothing would change.
Yeah, so the rate wouldn't change. Correct. So, like your concentration would change, but then the rate doesn't change. That should be a tip off. But be careful. Don't just assume because the rate doesn't change that it's not. Because if I were at IB, I would make one where the rate doesn't change, but then like B changes, so then you have to like remove B's impact and then see what A's actual impact is. So be careful about that.
And there's no such thing as a third order
No.
loss at least?
There is no such thing as a third order for our purposes.
Okay.
Correct. Because collision theory says only 2 things can collide at once. So the maximum possible order you can have is 2.
Why though? Why does it say?
Just because the probability of 3 particles colliding with the correct orientation and the right amount of energy is super unlikely. So it's not even worth trying to calculate that. Yes, theoretically it might happen every once in a while, but we're talking about like trillions to 1 odds and stuff like that. Okay. Now, this is our rate law expression. Rate equals k times a to the first, b to the second. So if they ask you for the rate law expression, that's what you write. No numbers, just variables. That's what an expression is defined by in science and in math. Now, the next part is solving for k, and solving for the units of k, which is also difficult. Okay? To solve for k, what do we do here? How do we solve for k using the data that we have already? Just find one trial and plug it in. It doesn't matter which one, you should get the same answer. So let's use the first trial. The first trial says 2, 1, and 4. So I'm going to plug in rate of 4 and k, and this is 2 to the first and 1 to the second. So therefore k is 2, lowercase k is 2. But k has units.
The unit differs for each one.
Okay, right. So here's what you have to think about it. The purpose of any constant's units is to make the units match on both sides. That's the only reason you have units on both sides. Okay? So it's important if you look at the units of everything to figure out what units you're missing and what units you need. So here's what I do. I write the expression again, but with just units and see what I need to fill in the blank. So what I do is this. I say my rate is molarity. Did I say per second? Okay, molarity per second. K has to be some unit. My unit of A is what? Molarity to the first. What's my unit for B? Molarity squared. So therefore this is molarity cubed. Because molarity to the first times molarity squared is molarity cubed. What do I need to multiply molarity cubed by to get molarity per second? What do I need to multiply molarity cubed by to get only molarity per second? Pancho.
1 over molarity squared times seconds.
Exactly. 1 over molarity squared times seconds.
And this is where we get into the whole decimeters and negatives.
Yes, so then you have to expand m. Like when I'm doing the work, I just write capital M and I sort it out the end. So this is my unit for K. 1 over molarity squared times seconds. And now you have to expand that out. So molarity squared is 1 over moles per decimeter cubed squared times seconds. And when it's in the denominator, you have to flip it to the top. So this ends up being decimeters to the 6th over moles squared times seconds, which then is written in one line as decimeters to the 6th, moles to the -2, seconds to the -1. You don't have to write it that order. You can write moles first. It doesn't matter, but that's your unit. Yes?
So is the overall order of those 3?
Yes, the overall order of the reaction is 3, and that does kind of relate to your K unit as well, but I'd rather not. I'd rather you work it out this way to avoid any mistakes. So that's the way I do it. I just write all my units out and go, what does unit K have to be to make it sense? And if you follow along that, you should get it right.
Is there not another way to do it where it's like you get the, wait, what's the base unit when it's first order or zero order?
If it's zero order, there's
It's mole.
it's moles per second. It's moles per unit time, because in zero order there's no unit on the concentration, so then it's the same.
Okay, because I remember the way we did it last year was like.
Yeah,
moles
I know.
per
Like,
times.
I know what they told you. What they told you was you take the overall rate order, and you subtract 1 from that exponent, and that becomes the exponent of your molarity. Like, because it's 1 over, like, cause like really, if you think about it, Pancho, like Sabrina said, this is third order, right?
Yeah.
You need to have 1 molarity left over, so really the exponent on the bottom is 1 less than the overall rate order.
Oh. The way I remember doing it was like you got the base, so it was like molarities per second, and you multiplied, I think it was like decimeters cubed, or moles per decimeters cubed by the order, and then you would multiply together. I can't remember.
Yeah, that's why I don't teach it that way. Because it doesn't, like,
It's, yeah, it was just really
yeah,
weird.
it's a little convoluted.
How
I
many
remember
different?
memorizing it.
So, yeah. So sorry, Doris.
So when they ask you for the rate law expression, do you have to solve for K?
That is usually a second step afterwards.
Okay.
So the rate law expression is just all variables. So in my experience, what they'll do is they'll give you data, and in part A, they'll say, determine the order with respect to each reactant. And part B will say, state the rate law expression for the reaction. And then part C will be, calculate K including its units. It'll be in that order. Yeah. Tyler.
How many possible units could K have?
Well, depends on how many possible overall orders you have, right? So if you have 0 overall order, that's one type version. If you have 1 overall order, 2 overall order, 3 overall order,
What's the
Well,
I'm just wondering, like, would it be beneficial to memorize each one, or is it easier to just work?
I would work it out. Because if I'm the IB, again,
They want to see the work.
if I'm the IB, I know what a student is going to try to memorize for the test. And so a lot of students will probably memorize up to 2nd or 3rd order, and what am I going to do on a test? 5th order. And see if you can figure it out. That's what I would do. Yes, yeah, Pancho.
The one thing also, can you scroll up a little bit?
Yeah, sure.
For the one where you calculated the rate and you did all the math going through it,
Yeah.
didn't you just look at the table, see what doubles and
Yes,
and then
that's the shortcut.
Oh, okay.
I'm showing you this way because this way is foolproof no matter what scenarios they put in the data table. It's harder to do the shortcut when you can't find constants across the rest of the reactants. So this is your fallback plan. You know, in chemistry, I've always tried to teach you 2 ways to do it, one way that's fast and one way that's foolproof. You know, and if you don't, because I feel like stress is the best memory eraser. You know? And so if you know this way, it always works. Always. Okay. Questions about all this? Okay. Now, here's the thing about the order of reactions, okay? And this is where it ties back to mechanisms. Okay? The order of reactions must be reflected in the rate determining step. Oh, that's this 2 words. Rate determining step, the RDS, which is also known as the slow step of the mechanism. So if you figure out the rate order, if anyone suggests a mechanism for that reaction and it doesn't match your rate law, then it can't be a suitable mechanism. And this is what I mean by that. Okay? The exponents of your rate law expression should equal the coefficients in the slow step. Because here's the idea. Okay? Every reaction has fast steps and one slow step. And this slow step is what bottlenecks the whole speed of the reaction. And wherever that happens in the reaction determines how fast the reaction can go. It's kind of like a freeway, right? If you are on a 4-lane freeway and it goes down to 2 lanes and then goes back to 4 lanes, okay? And if I ask you, well, what's the maximum speed you could go through that freeway without slowing down, you would have to figure out how fast you can go through the narrow part, and you just say that speed the whole time. It didn't matter how fast you go, you end up being slowed down by that bottleneck in the middle. That's what a reaction does in chemistry. The fast steps don't matter when you're measuring it because you don't notice those. You notice the one that slows down, and that's the one that you actually observe. And so what I mean by it is this, okay? Let's go back to, let's look at a reaction like this. Let's say this is a 2-step mechanism, okay? And so the overall reaction here is 2A plus C yields D. If my first step is the slow step, then my rate law better reflect those reactions in that slow step. So if I look at this and I say that's my slow step, my rate law should be rate is equal to K times A squared. If that's my slow step. That has to match. If this were my slow step, what would you think your rate expression would have to be then? If the second one's a slow step, what would my rate law expression be then? B to the first times C to the first. And that would be sensible, okay? But not 100% correct. Because what is B? A squared, yeah. And it's also an intermediate. You can't have intermediates in rates of reaction. So, like Noah said, B is really represented by 2A. Because B is made from 2A. So therefore, this rate actually becomes rate is equal to K times A squared times C. And that's how you get an overall order of higher than 2. Yes, Ginevra?
Is the slow step the one where the intermediate is made?
No. The slow step is the step of the reaction which has the slowest rate overall. So the slow step doesn't have to have an intermediate in this case. Okay. But in these cases, we are seeing one. Yes?
How do you know which step is the slow step?
Okay, so that's a good question. There's 2 scenarios there. One, they tell you. Like they could label it as a slow step and they have you figure out the rate law. Or 2, you figure out the rate law and then you have to relate that to the mechanism, say, this must be the slow step according to my rate law. So for example, up here, actually maybe that's not a bad example here, but so what they might do, Claire, and I've seen this, is they might walk you through and solve a whole rate law, right? And figure out the orders, and then say, part D, a student suggested this mechanism for the reaction. State and explain whether their mechanism was suitable according to your rate law. So you would say, well, this kid thinks this step is a slow step, but that doesn't match my rate law, so it can't be right. So let me show you for example.
Wait, what?
Okay? What?
How are they both slow?
No, Marcus. I'm saying if they're 2 separate scenarios. So I'm saying if this were the slow step, Marcus, this would be the rate law.
Different
There we go.
scenarios.
Oh, okay, gotcha.
If this was a slow step, okay.
Oh wait, if it isn't the slow step, then that isn't the rate.
Correct. It's not the rate determining step.
Yeah.
Because it's so fast that it doesn't actually affect it.
Oh, I mean like that isn't the rate. No, so even if the first one isn't the slow step, the rate to the right is still the rate expression for it.
No, only if it's a slow step. Only if it's a slow step.
And
Hence the term rate determining step. The one slow step, elementary step, is what determines the rate of the reaction. Okay, yes, Chloe.
So as long, if they tell you which is the slow step, you don't need to have to go through
Nope,
like the
correct.
thing to find it. It's just
Correct.
the coefficient.
So, like Chloe said, if you are given the mechanism and I tell you what the slow step is, you can figure out the rate law without doing any math. Correct. So, like for example, let's say we have something like this. A plus B yields C, and then B plus, or let's say A plus A yields D. I don't know, I'm just kind of making that up. And so my overall reaction here is 3A plus B yields C plus D. I'm just making that up. Okay? So let's say a student suggested this rate law, this mechanism. This is kind of back to Claire's question as well. Let's say, Claire, you figured out that your rate law was A to the first, B to the first. Let's say that's what you figured out to be. Now, if that's your rate law, and this is the suggested mechanism, which step must be slow because that's your rate law? Which step should be slow of these two? The first one. Why the first one, Claire?
It just,
There's both of them and they're both one of each. Right. So if this is my rate law, then that tells me that this must be my slow step. Because they have to match. Does that make sense, Claire? Okay. Yes, Chloe.
So the slow step rates that, like in the first one, you said that the total rate, like reaction rate is K. So it doesn't, you don't find it with the total?
Nope. So that's the key thing. So the overall reaction has no impact on any exponents.
Okay.
So the only thing you're checking with the overall reaction is if it is the same reaction that you're trying to solve for. Like, so if they suggest a mechanism, you should check two things. One, does it add up to the right overall reaction? And two, does their slow step match your slow step? And if the slow step is the second step, then you're allowed to substitute from the first step. So like up here, we were saying here, like if you have an intermediate in your reactants, you're allowed to substitute a real reactant for that if it's in a step before. It's a lot to take in, I know, I'm sorry. But we're kind of trying to cover all of this in that. But so the rate law is directly related to the slow step. Questions about that? Okay. Again, like I said, I know we're rushing through this. This would usually take me probably about a week and a half to cover in class. So we're going through this because you've seen it a little bit, but I don't expect you to all take all of it in at once, but at least expose to it so that you can review it later on and hopefully make some more connections. Okay, the last thing we're going to talk about today is the Arrhenius equation. Tomato, tomato, I'm right. Okay, so I'm kidding. I have no idea how to pronounce it. I just always said Arrhenius. I think it's the coffee talking. Okay, I don't really drink coffee a lot, but like the last 3 days I've had like 5 cups of coffee. And I hope I don't start an addiction here. Okay, so okay, Arrhenius equation. The idea of the Arrhenius equation is to calculate the activation energy of a reaction. Okay? And there are several ways to write the equation. And you see 3 different ways in the IB data booklet about how to write it. I prefer this version of it. ln of k is equal to negative EA over RT plus natural log of A. I prefer this version. Okay? Now, the reason why I prefer this version is because this version is set up the most closely to the way the graph is. Because what I want you to see here is that this is just a y equals mx plus b equation. That's all this is. Let me reorganize this a little bit. So this is really natural log of k is equal to negative EA over R times 1 over t plus natural log of A. This is your y, this is your m, this is your x, and that is your b. And so when you graph this, you're going to be graphing natural log of k versus 1 over t. And the slope will equal negative EA over R. And once you figure out the slope, you can solve for EA based on that. That's why I like this version of the equation best. Because when you graph this, I'm gonna not like sketch one. I'm gonna put one on here. But so let's see. I'm trying to see if there's one that I thought. Yes.
What does the A specifically?
We're gonna go into that a little bit. Okay, that's a good question. We were gonna talk about that in a second. Okay. Okay. We'll do this one. Okay. So, the way you do it is this. Okay? You calculate the natural log of k, the rate log constant. I don't know why it's capital K, but natural log of k, the rate log constant, on the y, and then 1 over temperature on the x. Now, please be careful with the units on the axes. Yes, Pancho?
Why is it 1 over t? Like, that's the one part I never.
Oh.
Does it go into like the derivation of the actual formula?
Yeah, like it's the way you linearize the equation. Like it's like inversely proportional to temperature, like the natural log of k is. Because if you think about it, the larger the k, actually no, hold on a second. Because you have a negative there, the larger the k, the more negative the k value, the natural log of k is. So then you get a line for that. I'd have to look back on the derivation. I'm not exactly sure about that. But so, careful on these graphs because sometimes the IB will manipulate the axes down here. So if you notice on this graph, it says 1 over t, but the number here is times 10 to the negative third of the actual value. Okay? So this is 3.30 times 10 to the negative third. So pay attention to that, because if you don't write that, your answer will be off by a factor of 1,000. Right? So that's a significant difference. So pay attention to the units of the axes. Okay? So we graph natural log of k versus 1 over temperature. Now, we pick 2 points on here. Let's say 0.30. That's a little slope down. That's probably good. And we'll pick, I don't know, oops. This one, like this. So I just picked 2 points, and I'm going to find the slope of that graph. So this point right here is, x is 3.30 times 10 to the negative 3. And y is negative, let's say 31.90.
Is this one of those things where the IB gives you a lot of leeway when you're
A little bit, yes. Like the grid lines will be pretty distinct, so it'll be easier to read. This point right here is, let's say, 3.41 times 10 to the negative 3. comma, negative 32.60. We'll say that. Okay. So we calculate the slope of that. So rise over run. So this will be negative 31.90 minus negative 32.60 over 3.30 times 10 to the negative 3 minus 3.41 times 10 to the negative 3. Okay. While you're writing that, I'll calculate that. I was seeing if anyone had a calculator out.
6,000.
Oh, I do. Me and Ginny both.
Wait, what?
It's about 6,000.
Okay. let me double check the exact answer here so we can kind of carry it on. But it's about, Mohammed says it's about negative 6,000.
Looking for it on the order and
Okay.
okay.
Wait, what?
Buffet, calculate it.
Oh, yeah, I got you.
Wait, yeah, send it.
Negative 3
Is it 10 to the 4th?
Wait, let me think. Wait. So everyone's looking at me.
10 to the 4th.
I got, okay, yeah, that's correct, but I got negative 6,360.
Okay.
Is that what you got?
Yeah, I got it. Okay. That's slope. That's the slope of the line. Okay. Now, according to our equation up here, that value is equal to negative EA over R. Okay. So if we set that equal to negative EA over R, which is 8.31 joules per mole Kelvin, units are really important. So I can solve for my activation energy now because I multiply that by 8.31. No, not on the IB. Okay, 52,881.8 joules per mole Kelvin. Or 52.881 kilojoules per mole Kelvin.
Mr.
Yes.
Do we need to worry about sick days?
I will say this. If you really want to be safe on this, I would say yes to an extent, but unless the question explicitly says to the correct number of significant figures, they give you one significant figure either direction. So I would say, unless they explicitly state significant figures, go to 3 significant figures, you should be safe. Yes, Ginevra?
For questions like these, will it be more like they give a graph and you have to find the activation energy, or you have to plot the graph?
No, I don't think they'll expect you to plot the graph. I think that's, in their minds, that's a waste of time. So you will be given the graph, and that way there will be less room for error there. So you'll be given the graph. Tyler?
Where did gas constant?
Gas law constant, yeah, R. So the activation energy of this reaction is 52,881 joules per mole Kelvin. Okay, now, like Chloe asked earlier, A has a significance in this. Okay, natural log of A, we said, is B. And what is B represented in an equation? Y-intercept. So let me write this down here. So natural log of A is the y-intercept. Okay? Now, let me say this, okay? We are measuring versus temperature on this, and how increasing temperature increases the rate of the reaction, or the rate law constant. Okay? Now, at the y-intercept, what kind of temperature do we have theoretically at the y-intercept? Think about it. No, remember, because the x-axis is 1 over T. So, as temperature is going down, or sorry, as 1 over T is going towards 0, T has to be getting bigger. Right, so you're right, 1 over T is going towards 0, but T itself is getting really, really big. Okay? Now, if T is getting really, 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 really big, what does that affect about the particles in the system? They have a very high energy. In fact, at infinite temperature, every particle has enough energy to react. Every particle has enough energy to react. So what's the only variable that you have left? Nope. Nope. What's the other factor that happens in collision theory?
Activation.
No, that's energy.
Oh,
Orientation.
Collision orientation. So at infinite temperature, there's only one factor that's left that you have to worry about, and that's orientation. So A is that idea. So A is called the frequency factor.
Mr. Sean,
Yes.
but if you gave a reaction long enough, wouldn't everything eventually get to the correct orientation?
Well, over time, yes, but it wouldn't happen instantaneously.
Okay, but that's why it has like the gradient, like the plateau back on the graph.
Yes.
before.
Yeah. So with these, we're talking about, for all the rate law expressions, we're talking about initial rate, the fastest maximum rate possible, and then it goes off lower later on. So A is known as the frequency factor. And what it does is it takes into account the frequency of collisions with the correct orientation.
And is it something that's unique to
Every single reaction, correct. So the A value is unique to every single reaction. And so you could calculate it using the equation and via all the other values as well. But most likely they're going to ask you what does A represent? And you would say it factors in the frequency of collisions with the correct orientation. Yes.
Why exactly does the orientation matter?
Okay, because remember, when we were talking about earlier, for a bond to be formed, the two atoms that are forming the bond have to collide with each other. So if you don't collide in the correct way, then that bond can't form.
That's my question though. Why is that the bond forming?
Because they're not physically touching. So like, if you go back to what we were talking about earlier in S cell, here, if this green particle collides with this pink particle, there's no way it's going to form a bond with the blue particle. Because the electrons aren't overlapping and sharing and transferring that bond. Yes, Mohammed?
What's the unit for?
I don't believe there is a unit for that. Okay? So you won't actually, I don't believe they'll actually ask you for a unit for that. It's kind of strange because I don't think it's not an energy, it's just number of collisions. So I don't think there is like,
Number of collisions per how many?
yeah, but then like if you're looking at the equation, then how do all those units match up to what lowercase k is? Like, because natural log of k, like what are the units of that? So I wouldn't be concerned with the units of that. Yes, Chloe.
So is the frequency the same throughout all temperatures, or does that change? Like for orientation?
The frequency factor stays the same.
And like what is the frequency factor exactly?
It represents how many collisions have the correct orientation. Because at infinite temperature, every collision that has the correct orientation will react.
So it's like proportion.
Yeah, it's kind of a proportion. So it's saying, okay, this is how many collisions per unit time must be colliding correctly because this is how many would react at infinite temperature.
So it's per unit of.
No, but like it's a natural log of that. So A
Yeah.
itself might be per
Yeah.
unit time,
Okay.
collisions per unit time, but you're not going to write the unit for that out in the value. I guess so. Yes.
No, I think it got answered. But so A is the value, the number value of A is the number of collisions.
A number of the frequency of collisions that are the correct orientation.
Per unit time.
Sure, per unit. Well, frequency is that's redundant. That's redundant because frequency is already implied unit
So
time.
basically, it's just a number. It doesn't really.
Yeah, it's just a value that says if you had infinite temperature, this is how many successful collisions you would have. But you don't always have. You don't have infinite temperature.
It's like okay, so it's
So,
like an
like,
arbitrary scale, basically.
So now that I think about it, here's the idea. This is the optimal, like the infinitely maximum rate of reaction, the rate law constant here. But every time you have a temperature that's lower than infinity, you reduce the overall value of it by this factor, right? So if this is like 100%, every time the temperature is less than infinite, then you reduce the potential of the reactions occurring, so the number keeps getting smaller and smaller and smaller. So as temperature goes down, the quantity, the sum of that gets smaller and smaller and smaller. It's less chance that the reaction rate slows down.
Oh yeah, because as the temperature tends towards infinity, then K would equal A.
Yes, exactly. Exactly. Yes.
What I don't understand about A is your frequency of collisions is going to depend on how many particles you have in a certain amount of space and the pressure and the volume
No,
of the space. So
it's not in that scenario for a couple of reasons. One, with the frequency of collisions, if you're at an infinite temperature, it almost doesn't matter how many particles you have in that connect, because they're moving so fast that they're not going to, the distance they have to travel to collide with each other is going to be negligible.
But what about, let's say I've got 4 particles in this room at
Right.
infinite temperature, and then 4 in a highly pressurized, very small container. They're going to react 10 times.
Well,
much more frequently.
we're assuming at infinite temperature that they're moving so fast that the distance, the actual distance between the particles is negligible. Like they're moving that fast. So we're not worried about the proportion and the volume and stuff like that. Yes, Mohammed.
Okay, but if you have 4 particles versus 1,000 particles,
Right.
Yeah.
how would the frequency
Okay.
change?
So in that scenario, with that, I would say the frequency factor, I guess, would have to be it'd have to be proportional to how many particles you have in there. Like that constant would have to be in that idea.
So if I have-
But I wouldn't say the volume itself necessarily. It's just really the number of particles.
But let's say I've got 3 molar HCl and then another reaction with 1 molar HCl.
Right.
3 molar is going to have a higher A value.
No, because we're talking about number of collisions per mole of particles. So
So it
Yeah.
matters how many particles are in a mole.
I would say so, yeah. Okay. So, that's that. Another way to write this, okay, another way to write this equation that's in the data booklet that is more likely to be to use to be solving for this is this version of it. K is equal to A times e to the negative EA over RT. Okay? That's another version of the same equation. It's just no natural logs to kind of simplify it. I would say this version is easier if you're given values and you're trying to solve for the rate law constant or something like that. But if you're given a graph, you should use the other version, the y equals mx plus b equation.
Would it not be A plus?
No, because remember when you take the log of something, times becomes plus. Yeah. The law of logarithms and stuff like that. So, yeah, so this is just another rewriting of it. You don't have to use it. You could theoretically use the other equation for all scenarios. Yes?
So you said K is the
Rate law constant.
What exactly is that?
The rate law constant is the rate of the reaction at a given temperature that is inherent to the reaction regardless of the concentration. So if you look up here at these rates, this is what you multiply the concentrations by to get the actual rate here. So that's a constant for every reaction that you multiply the concentrations by to get the rate here. So if the concentration of this were 1 and 1, that constant is what actually gets you the correct rate of reaction. So it's like a factor. Y is because when we do experiments, we find the rate and we find the concentration, and this is the only value that makes those things together that equal to each other. That's the kind of the missing link. You know, kind of like how in ideal gas law you have pressure, volume, temperature, and moles, but you need R to make them equivalent to each other. That's what K is here. K is what links the concentration to the rate of the reaction. And that rate law constant changes with temperature. That's why we have this graph here. So as temperature goes up, rate goes up as well. So your rate constant also goes up.
So in this case you're just looking at the rate, like the general.
The rate law constant.
Yeah, because the coefficients remain
Yeah.
constant, so you're looking at K to see
Yes. How it changes, correct. And that relates to your activation energy. Okay. So, one last thing, and I was just saying this to Chloe just before we kind of go. as temperature increases, the rate law constant will also increase. That's why you get this version of the graph here. When you inverse temperature and you next log K, you get this graph. So no matter what kind of reaction you have, if you increase temperature, the rate law constant will go up. Okay, that's always true, because you're going to have more particles that react. That's not the same as equilibrium, because equilibrium depends on whether it's exothermic or endothermic. But rate of reaction always increases with temperature. Your yield may not increase, but your rate will always increase. So you want to make a note here that increasing temperature will always lead to an increase in the rate law constant. That's kind of an important concept.
I thought temperature also shifted there.
Wait, sorry?
I thought temperature also shifted to equilibrium.
Yeah, but equilibrium is capital K. And that's a separate
Why
concept.
do they do that?
Does that?
Well, no, it only shifts to the right if it's endothermic.
Yeah, but like it's still, so does that affect
The rate, no. Whether it's endothermic or exothermic, the rate will always increase. The yield will decrease or increase based on the type of reaction. Okay, that's it for today. Thank y'all very much. Hopefully y'all have a good week.